Hello! So, in this video we're going to be covering the Cauchy Criterion for infinite series. So, just in terms of parlance for sort of mathematics in general, in case you haven't run into this much yet, a criterion is sort of a term we use for a sort of test to show something works. It's typically reserved, although not always, for situations that are both necessary and sufficient, meaning that they are sort of in some sense, the cleanest, nicest test of its type. It doesn't have any extra hypotheses that it doesn't need, and it gives you sort of exactly what it claims it wants to give you. So in this case, when we talk about the Cauchy Criterion, we're saying that we want something that is equivalent, a way of showing convergence. So the theorem, as it's actually stated, so if we have some series for sort of consistency in notation, I'm using this L as the starting point, but it doesn't matter. So k starting somewhere to infinity of ak. We say this converges if and only if, meaning, again, bidirectional implication. So it's equivalent. So for every epsilon greater than 0, meaning, in some sense, for arbitrarily small, uncontrolled by you epsilon, right? Anybody could throw you one, you could do this. There is a natural number n, so that if we pick little n and little m, and for the sake of sort of argument, we will say label the bigger one n and the smaller one m, but they're both at least n in size, right? And sort of the point here is that if you pick any n and m bigger than n, where the bigger one is labeled n, again, natural numbers, then taking the sum of those terms, right, from the little one up to the big one, am up to an, that sum in absolute value, the result after summing them up, not the sum of the absolute value of each, but the absolute value after, that's actually really important. The sum of that is less than epsilon. So the proof for this is really, I'm not even really going to prove this so much as I'm going to point out that this is actually explicitly, this is the Cauchy criterion for the convergence of sequences. And in fact, this is what we've done here, which it may not be obvious, that's what I'm going to do, is we've written a series in terms of Cauchy sequences. And that's not an accident. There's a reason why this is the Cauchy criterion. It's the same guy doing the same technique, just applied in different settings, okay? So what I'm going to do by way of proof is I'm going to show that that's exactly equivalent. What this statement is exactly equivalent to the statement of the Cauchy convergence of sequences. So recall, meaning we already know this, but just I'm going to use it to draw your attention here. So recall Sn, I'm going to use lowercase n because I'm going to be using this later. This is an plus an minus 1 plus ... all the way down to the first thing, which was L plus 1 AL. Okay. So I'm going to literally rewrite this. So this says, this thing, well, what is this? This is saying that the limit of the partial sums, right? Because that's exactly what this is. So this is say the limit as capital N goes to infinity of, oops, sorry, not A. I don't know if you can see that on there, but smudges everywhere. Sorry, so capital N, right? This was exactly what it means for this to converge, that this thing converges if and only if what? Well, for every epsilon, maybe I should do, just because I'm going to use n here to be consistent with this, I'm actually going to maybe make this an m, just to keep it out of the way, because I want to try to be as consistent letter-wise with this statement as I can. So for every epsilon greater than 0, there is capital N in the natural numbers, so that if n and m are, so I'm writing it a little bit differently to hammer home the Cauchy sequence bit. So I'm going to say n and m, at least n, and I'm going to say n greater than or equal to m. But again, I want to stress that really what I'm saying here is pick two numbers bigger than n, label the bigger one n, right? I'm not supposing that I needed to pick an n, pick an m, and then hope n was bigger. I'm saying pick two numbers, make the bigger one n as a label. Okay, so that's not an issue. That's always easy to do, right? Because it's a labeling thing. And also, so with n and m, natural numbers, right? Because I want to use these as indices, so obviously that would make sense. So it's gonna be a little bit fudged up. I'm gonna have a little bit of sloppiness, but I'll point out why it doesn't matter. So I have that, then so I'm going to do it from, instead of am, I'm going to go from am plus 1. But this isn't a problem, and I'll explain why. So what is this? Well, if I took the sum up to an, that would be s little n. And if I took from am off, that would be subtracting sm. Right? But this is exactly this thing, except that now I'm starting at k equals, I just realized I flipped those. Let me fix that in a second. So this would be k equals m plus 1 to n of an, of ak, excuse me. That is less than epsilon. So let me fix that before I go any further so I make sure I don't forget. So if you notice this, kudos, because this was an error. So this is m was the smaller thing, n was the bigger thing. Okay. So my claim is it's not any worse to add there. And the reason why is the m was just chosen sort of arbitrarily, right? So instead of choosing the m that I would have picked, I could choose one smaller, and that way when I add one, I get back to the m, right? Meaning that here, even though I'm adding one less term, because these things are sort of arbitrarily chosen to be anything at least n in size, I can choose anything at least n in size here and sort of choose the right thing to reflect this thing here, right? So the fact that I'm adding one fewer term isn't really a problem because these things are arbitrarily, I have arbitrary number of terms that aren't in my control in the first place, so it's okay. So with the caveat of that small little hiccup from notation, which I didn't have to do, but I'm doing for the sake of showing clearly the parallel. Now that I've rewritten this in terms of that, let's see what it actually says in terms of sequences, right? So in sequences, I'm saying that the limit of a sequence converges if and only if, for every epsilon, there's some number that if I pick 2 points, 2 indices bigger than that number, the difference of those two sequence values, Sn and Sm, is less than epsilon, right? The Cauchy tail, the tail pieces, if I pick any two in the tail after capital N, they are at most epsilon apart. That is literally the Cauchy criterion for the convergence of sequences. This is, in the book, I think they mark it as a theorem that says that as long as we're in the real numbers, which again, this is a series of real numbers, Cauchy sequences, so this is i.e. a sequence of real numbers converges if and only if it is Cauchy. Right, so sequence of real numbers converges, that's this thing, if and only if, and this definition is exactly saying that it's a sequence, a Cauchy sequence. And this is in chapter 2. So, in fact, I don't actually need to prove this because it's already been proved in the section on sequences, because all this is exactly that Cauchy sequences converge in the real numbers, but written in the parlance of infinite series. Okay? And as a quick historical footnote, as I mentioned in the intro video, Cauchy was the one who did a lot of the work on formalizing the rigorous nature of converging in series, in doing real number, real valued series, as well as complex valued series and some other stuff. So it's not surprising that he would have not only have this criterion that he developed, but that it would be very similar to the notions that he developed in terms of rigorous convergence sequences. Like, he was doing both of these things at the same time because he realized that the best way of looking at series was as sequences, right? The sequence of the partial sum. So in terms of his actual mathematical sort of research, he was doing both of these ideas at the same time. So it's not surprising that they are very closely paralleled in how they're defined, because he was doing them together. All right. So that's all there is to it. It is that straightforward. That's it.